The year is 2022. Over the coastline of North Wales, Squadron Leader Gregor Ogston is flying a BAE Hawk jet at 400 miles per hour, 100 feet above the sea. He is Red 6 in the Royal Air Force Red Arrows, the synchro leader responsible for the most dynamic and dangerous maneuvers in the team's display. Right now, he is racing toward Red 7, Flight Lieutenant James Turner, who is flying directly at him from the opposite direction. The two jets are closing on each other at a combined speed of 800 miles per hour, separated by seconds, and the crowd on the beach below has no idea what is about to happen. Ogston is running down the display line, locked onto his heading for a maneuver called the boomerang, when he sees something in his peripheral vision, a large seagull directly in his flight path, close enough that his brain barely has time to register what it is. He closes his eyes and ducks. The gull hits the right side of his canopy at 400 miles per hour. The impact is instantaneous. The canopy does not crack. It does not spiderweb. It shatters completely. Glass, bird remains, and debris blast into the cockpit and slam into Ogston's helmet with enough force to rip the oxygen mask clean off his face. The noise is unlike anything he has experienced in 17 years of flying. He would later describe it as what it would sound like to drive a car at 70 miles per hour with every window fully open, except at 400 miles per hour, with earplugs in and a helmet on, and the sound still deafening enough to make communication impossible. If you're fascinated by the engineering behind military aviation and the extreme challenges that pilots and designers face at the edge of what physics allows, make sure to hit that subscribe button and like this video. Your support helps us bring more of these incredible accounts to light. Red 7 is still closing on Ogston from the opposite direction, but the two pilots had already committed to their miss distance before the strike, which means they are on heading and going to pass each other regardless of what happens next. Ogston trusts Turner completely. He has no choice. He is essentially flying blind. Turner rockets past Ogston's left wing. The immediate collision risk passes. But Ogston's problems are just beginning. His mask is dangling. Without it pressed against his face, he cannot transmit on the radio. To key the microphone, he needs his left hand to press the transmit button. To hold the mask against his face so the microphone can pick up his voice, he needs his right hand. That leaves 0 hands on the flight controls. For a few critical seconds, Ogston flies the Hawk with his knees while holding his mask to his face and pressing the transmit button simultaneously. He manages to get out a brief call, but the wind noise in the open cockpit is so severe that air traffic control can barely hear him, and he can barely hear them. Turner, flying alongside as Red 7, realizes what has happened. He slides into formation alongside Ogston and takes over communications. Turner talks to air traffic control on Ogston's behalf, clearing the airspace and arranging the emergency landing at Hawarden Airport. He escorts the damaged Hawk all the way down. Ogston lands safely. Fire crews are waiting on the runway. His helmet is destroyed. The canopy is gone. There are chunks of seagull embedded in his flight equipment. He walks away without a scratch. I want you to understand why that outcome is remarkable, because 58 years earlier, a nearly identical bird strike killed one of the most promising pilots in American history. And the reason Ogston survived in 2022 when that pilot did not comes down to a single engineering decision that transformed what a canopy is made of and what it is designed to do. The year is 1964. Captain Theodore Freeman is making a routine approach to Ellington Air Force Base in Houston, Texas. It is the morning of October 31st, a Saturday, and Freeman is returning from training at the McDonnell Douglas facilities in St. Louis. Freeman is not just any Air Force pilot. He is a NASA astronaut, one of 14 men selected for Astronaut Group 3 just 1 year earlier. This is the group being trained for Apollo. 10 of Freeman's 14 classmates will eventually go to the moon. Buzz Aldrin is in his group. Michael Collins is in his group. Al Bean, Gene Cernan, and Dick Gordon are in his group. Freeman is 34 years old. He has a master's degree in aeronautical engineering from the University of Michigan. He has logged more than 3,300 hours of flight time, including 2,400 in jets. He graduated from both the Air Force Experimental Test Pilot School and the Aerospace Research Pilot School at Edwards Air Force Base. He is, by any measure, one of the most qualified pilots alive. He is flying a Northrop T-38 Talon, the world's first supersonic trainer, a sleek twin-engine jet with tandem seating and a single-piece canopy made of plexiglass. At 10:46 that morning, Freeman calls Ellington Tower and reports that he is 5 miles southwest, inbound. He receives no response. 30 seconds later, he reports that he is breaking out to the east. 2 airmen on duty in the air traffic control tower are watching his approach. They see what happens next. A snow goose flies directly into the path of Freeman's T-38. The bird strikes the plexiglass canopy. Unlike Ogston's polycarbonate canopy 58 years later, which shattered into fragments that stayed relatively contained, Freeman's plexiglass canopy does something far worse. It fractures into long, jagged shards that are immediately swept backward by the 300-mile-per-hour slipstream and ingested directly into both of the T-38's General Electric J-85 engines. Both engines flame out instantly. Freeman is low. He is on final approach, which means he is slow, close to the ground, and pointed at the runway with no power. The 2 tower observers see no evidence that Freeman attempts to eject, but even if he had, he was too close to the ground for a parachute to deploy. The T-38 pancakes onto a public highway 1 mile south of the Air Force Base. The impact is violent and immediate. At 10:58 that morning, Dr. Charles Barry, chief of the Manned Spaceflight Center Medical Operations Office, declares Captain Freeman dead at the scene. Deke Slayton, the chief of the astronaut office, drives to the Freeman home in Nassau Bay to tell Faith Freeman that her husband is gone, but he arrives too late. A reporter has already shown up at the door. Faith Freeman learned that her husband was dead from a journalist who wanted a comment. NASA changed its notification procedures because of that moment. From that point forward, when an astronaut died, astronauts would be the ones to deliver the news, and they would get there before anyone else. Theodore Freeman became the first member of the NASA Astronaut Corps to die in the line of duty. His classmates went to the moon. He is buried in Arlington National Cemetery. But here is what investigators found when they examined the wreckage and pieced together what happened. The snow goose did not destroy Freeman's aircraft. The canopy did. The plexiglass used in the T-38's canopy in 1964 was an acrylic thermoplastic called polymethyl methacrylate. It was lightweight, it was optically clear, and it had one critical flaw. When struck by a high-speed projectile, acrylic does not deform and absorb energy. It shatters into rigid, angular fragments, exactly like glass. Those fragments become secondary projectiles. In Freeman's case, the shards of his own canopy were swept into the engine intakes at hundreds of miles per hour. The ingested debris destroyed the compressor blades in both J-85 engines. The goose alone might not have caused a dual-engine failure. The canopy fragments guaranteed it. I find this particular detail fascinating because it reveals something that is easy to miss about bird strike engineering. The threat is not just the bird. The threat is what the bird does to the aircraft structure, and what the damaged structure then does to everything around it. A canopy that shatters into engine-killing fragments is worse than a canopy with a hole in it. After Freeman's death, and after a series of other bird strike incidents through the 1960s and early 1970s, military aviation engineers began a fundamental rethink of canopy materials. The question was no longer just whether a canopy could keep the weather out and give the pilot good visibility. The question was whether a canopy could survive a high-speed impact and still protect the pilot and the aircraft behind it. The answer turned out to be polycarbonate. Polycarbonate is a thermoplastic polymer that behaves completely differently from acrylic under impact. Where acrylic shatters into rigid shards, polycarbonate deforms. It bends. It absorbs energy by flexing rather than fracturing. Its impact resistance is staggering. In standardized testing, polycarbonate absorbs roughly 600 to 850 joules per meter in the IZOD impact test. Acrylic absorbs 15 to 20. That is not a marginal improvement. That is a 30 to 40 times increase in impact resistance. By the 1980s, polycarbonate had become the standard material for military fighter canopies. But the material alone was not enough. engineers had to figure out how to form polycarbonate into the complex curved shapes required for fighter cockpits, how to maintain optical clarity across the entire surface, and how to make the finished canopy resistant to the extreme conditions of supersonic flight, including temperatures ranging from -55 degrees Celsius to 120 degrees Celsius, pressurization loads, chemical exposure, and ultraviolet degradation. The F-22 Raptor represents the current pinnacle of canopy engineering. Its canopy is the largest single piece of monolithic polycarbonate ever produced in serial production. It measures 140 inches long, 45 inches wide, and 27 inches tall. It weighs 360 pounds. It has no canopy bow, which is the reinforcing frame that runs across the middle of most fighter canopies, because eliminating the frame gives the pilot unobstructed optics in every direction, not just straight ahead through the heads-up display. The canopy is 3/4 of an inch thick. It starts as two separate 3/8 inch sheets of polycarbonate that are heated, fusion bonded so that the two sheets meld into a single monolithic piece, and then drape forged into the final curved shape. The manufacturing process takes up to 60 days. However, that 3/4 of an inch of polycarbonate is not just sitting there looking pretty. It has been tested to withstand the impact of a 4-pound bird at 350 knots, which is roughly 400 miles per hour. The canopy must absorb the impact without allowing the bird to penetrate the cockpit. It must absorb the impact without generating fragments that could be ingested by the engines. And it must absorb the impact without deforming so severely that it interferes with the ejection sequence. Because if the pilot needs to punch out after a bird strike, that canopy has to jettison cleanly. That last requirement created its own engineering problem. During bird strike testing on the F-22, engineers discovered that the heads-up display combiner glass, which sits just in front of the pilot's face, would shatter the canopy when the polycarbonate flexed inward during a bird impact. The flexing canopy would strike the rigid glass of the HUD and crack. The solution was a rubber buffer strip mounted on the HUD that cushions the canopy when it deforms during a strike. A small detail, but the kind of detail that separates a pilot who walks away from a pilot who does not. Now, you might think that proving a canopy design works would involve computer simulations and materials testing on laboratory samples, and engineers do use those methods. But the definitive test, the one that has been in use since the 1940s, is far more direct. They shoot a dead chicken at it. The device is called a chicken gun. The formal name at Arnold Air Force Base in Tennessee is the S-3 Bird Impact Range. It is a large-diameter compressed air cannon with a 60-foot barrel that fires chicken carcasses at speeds exceeding 700 miles per hour into aircraft canopies, windshields, wing leading edges, and engine inlets. The gun was first developed in 1942 by the Civil Aeronautics Administration and Westinghouse Electric. Those first tests were revealing. The standard glass used in passenger aircraft windshields at the time, the same kind of glass used on the Douglas DC-3, was penetrated completely by a 4-pound bird traveling at just 75 miles per hour. The glass was not even close to adequate. The chicken gun at Arnold has been operational for more than 50 years. It has been fired more than 1,000 times. Its test subjects have included the canopies of the A-10 Warthog, the C-130 Hercules, the F-15 Eagle, the F-16 Fighting Falcon, the F/A-18 Hornet, the F-22 Raptor, and the F-35 Lightning. Every one of those canopies had to survive the gun before the aircraft could be certified for service. As one Air Force technician explained, the best thing to use to simulate a bird strike is a bird, and chickens are the easiest to come by. The process works like this. A chicken carcass, typically 4 pounds, is placed inside a balsa wood container called a sabot. The sabot centers and stabilizes the chicken in the barrel. The barrel is pressurized with compressed air behind a thin diaphragm. When the diaphragm is ruptured, the compressed air propels the sabot and chicken down the barrel toward the test article. As the assembly exits the barrel, a tapered section strips the sabot away, and the chicken continues in free flight toward the canopy. High-speed cameras capture every millisecond of the impact. Engineers analyze the footage frame by frame, measuring deformation, crack propagation, fragment dispersal, and penetration depth. The canopy either passes or it does not. Some engineers prefer their test chickens thawed to room temperature. Others, particularly in the Air Force, have traditionally used frozen birds, reasoning that if a canopy can survive a frozen chicken, it can certainly survive a living one. The frozen bird approach was eventually replaced by synthetic birds made of clay and plastic, partly due to concerns from animal rights activists, and partly because synthetic projectiles provide more consistent and repeatable test conditions. But the fundamental test has not changed since the 1940s. You want to know if a canopy can survive a bird? You fire a bird at it and see what happens. Major Justin Lee, an F-35 pilot, put it simply after watching his aircraft's canopy survive a chicken gun test. As a fighter pilot who flies this aircraft, I can say that it is definitely comforting that the canopy can survive an impact like this. What Major Lee was looking at was the direct descendant of a lesson written in blood over decades of bird strike disasters. Theodore Freeman's death in 1964 was not the last. It was not even the worst. On September 22, 1995, at 7:45 in the morning, an E-3 Sentry airborne warning and control system aircraft lined up on runway 5 at Elmendorf Air Force Base in Alaska. The aircraft carried the call sign UCLA 27 and had 24 crew members on board, 22 Americans and 2 Canadians. This particular E-3 had flown combat missions during Operation Desert Storm, controlling the intercept and shoot-down of 4 Iraqi fighter aircraft in western Iraq. It was a veteran aircraft with a veteran crew. 2 minutes before UCLA 27 began its takeoff roll, a C-130 Hercules had departed from the same runway. The Hercules disturbed a flock of Canada geese that had been roosting in the grass near the runway. The tower controller observed the geese becoming airborne and turning toward the departure path. He did not warn the E-3 crew. As UCLA 27 rotated for liftoff, the flock of geese, more than 100 birds, flew directly into the aircraft's path. Multiple birds were ingested into the number 1 and number 2 engines on the left wing. Engine number 2 suffered catastrophic failure. Engine number 1 compressor stalled. The cockpit voice recorder captured the crew's words. All the birds. Then, we took 2 of them. The crew began an emergency left turn to return to the runway. They started dumping fuel, but with a full fuel load and 2 engines lost on the same wing, UCLA 27 could not maintain altitude. The aircraft reached a maximum height of 250 feet, then began to descend. It crashed into a hilly wooded area less than a mile from the runway, broke apart, exploded, and burned. All 24 crew members were killed. The investigation found that the probable cause was the ingestion of Canada geese into the 2 left engines, but it also found systemic failures. There was no effective bird hazard program at Elmendorf. The tower controller had not issued a bird warning. The last runway check had occurred nearly 3.5 hours before the accident. 4 officers received administrative discipline for their failure to manage the bird threat. The UCLA 27 disaster remains the deadliest bird strike in United States military aviation history. An aircraft that survived a war was destroyed by geese. 24 families lost someone because a flock of birds was standing near a runway and nobody told the crew they were there. Between 2007 and 2016, the Air Force and Navy recorded an average of 5,600 bird strikes per year. The total damage from those incidents amounted to roughly $400 million over that decade. From 1988 to 2019, 217 aircraft worldwide were destroyed or damaged beyond repair by bird strikes. These numbers are why a single F-22 Canopy costs what it costs. These numbers are why engineers fire dead chickens at glass for a living. These numbers are why military-grade polycarbonate is manufactured to specifications that would seem absurd for any other transparent material on Earth. The canopy sitting on top of a modern fighter jet is not a window. It is a piece of transparent armor engineered to absorb the kinetic energy of a 4-pound projectile traveling at 400 miles per hour, distribute that energy across its surface without generating lethal fragments, maintain structural integrity for continued flight or safe ejection, protect the pilot from wind blast, depressurization, chemical agents, and lightning strikes. and in the case of the F-22, reduce the aircraft's radar cross-section through embedded metallic oxide coatings that make the canopy part of the stealth system. It does all of that while maintaining optical clarity above 90% in every direction the pilot needs to look. In 1964, Captain Theodore Freeman died because a single goose shattered a plexiglass canopy that turned the pilot's own aircraft into the weapon that killed him. The acrylic fractured into shards. The shards destroyed both engines. The engines failed. The pilot could not eject. In 1995, 24 crew members of UCLA 27 died because birds entered engines that could not survive the ingestion and because nobody warned the crew that the birds were there. In 2022, Squadron Leader Gregor Ogston flew a Hawk jet with a shattered canopy at 400 miles per hour, steered with his knees, held his mask to his face to transmit, and landed safely at Hawarden Airport because the polycarbonate canopy did exactly what 60 years of engineering had designed it to do. It broke, but it broke in a way that kept the pilot alive. The Royal Air Force awarded Ogston the Green Endorsement, its highest safety award. Air Chief Marshal Sir Mike Wigston presented it personally. Ogston said the award reflected everyone at the Red Arrows who played a role in achieving a safe outcome that day. He finished his 4-year tour and moved on to instruct the next generation of fighter pilots. Somewhere at Arnold Air Force Base, the chicken gun is still firing, and somewhere in a manufacturing facility, the next fighter canopy is being heated, fused, and forged into a single monolithic piece of polycarbonate that weighs 360 pounds and takes 60 days to produce. Because the lesson of Theodore Freeman, the lesson of UCLA 27, and the lesson of every bird strike that has ever killed a pilot or destroyed an aircraft is that the sky is full of things that want to come through the glass. The only question is whether the glass is ready. What I find remarkable about this story is how directly you can trace the line from failure to solution. A goose killed an astronaut in 1964 because his canopy was made of the wrong material. Engineers spent the next 2 decades developing the right one, and in 2022, over the coast of Wales, that material proved itself in exactly the scenario it was built for. 60 years of engineering, thousands of dead chickens, billions of dollars, all of it so that the next pilot who meets a bird at 400 miles per hour walks away instead of being carried away. That is what 3/4 of an inch of polycarbonate is worth.